Good afternoon to all. We are discussing the finite automata, and in that finite automata, we discussed about non-deterministic finite automata and deterministic finite automata. So far we have discussed about conversion of NFA with epsilon moves, that is non-deterministic finite automata with epsilon moves, to NFA without epsilon moves. The second conversion we have discussed, that is nothing but the NFA without epsilon moves to DFA, that is deterministic finite automata. And also we have discussed about NFA with epsilon moves to deterministic finite automata. In this lecture, we are going to start a new topic, and that is nothing but minimization of automata, finite automata. So minimization means what? Means we are going to reduce the number of states in the automata. So how to reduce the states in the automata? Because what happens if the automata has a multiple number of states, or if it has multiple number of many number of states, then it becomes very difficult to draw that particular automata, or to draw the state transition from one state to the another state. And it's very, one can say, the tedious work to understand the actual working of that particular automata. So it is necessary to minimize that particular automata with a fewer number of states, So in a simple language, we can describe like this: if initially the automata is suppose having 7 or 8 states, then these 7 or 8 states that can be compressed, or that can be reduced to 3 to 4 states, right? But this particular one can say minimization must has certain mechanism, must have certain steps. Means directly we cannot delete the states, or we cannot remove the states, but yes, there is a fixed number of steps. There are some methods how we are going to minimize the number of states in that particular given finite automata, so that it becomes easier to understand, as well as it becomes easy to one can say that it will be easier from that particular finite automata. So minimization of finite automata means reducing the number of states from given finite automata. We get finite automata with redundant number of states after minimizing the automata. So for this minimization, what we have to do here, first find out which two states are equivalent that can be represented by one state. Means it may happen that in automata, the two states on same or different input, they may lead to same state. Say for example, suppose there is a Q0 state and a Q1 state, and they go to, say for example, Q5 states. So instead of representing these two different states, Q0, Q1, can we represent as a single state Q0, Q1, and it will go to Q5 state on the same input symbol, for example, A? Yes, we can do this. So we can have the option, or we can have a proper procedure to minimize the number of states. So for that, we have to find out the equivalence between the states, or equivalent states. We have to find it out here. So two states. So when we can say that two states are equivalent or equivalence, how to find out the equivalence? The two states Q0 and Q1 are said to be equivalent if both Q1 on input X and Q2 on input X are final states, or both of them are non-final states of all where state, say for example, input belongs to the set of input alphabet. This X is nothing but your input alphabet, means it can be either A, comma B, or it can be 0, comma 1. It belongs to your input alphabet sigma, right? So one can say that if the two states, when we can say these are the equivalent state, or these are the equivalent state, when these states, they are final states, means delta means transition on the Q1 on input X, transition on Q2 on input X, they lead to final state. Means minimizing automata, we have to start in the reverse direction. Means we have to first find out which is the final state, this is the final state, and start minimizing that automata in a reverse way. Means starting from the final state, you just find out which two states lead to, means which two states they are coming to that particular final state. Say for example, Q0 and Q3. These two states on input A, for example, on input A, they leads to the final states, right? So input is same, the states are different, and the next state is the same. That is, next state is nothing but your final state. So instead of having these two state, I can combine this Q0, Q3, right, like this way, and on a single input, they can go to the final state. On the same input, they can go to the final state. Getting this point. So equivalence, we have to first find out it is very simple method. It is very simple. One can say steps are given. Just we have to find out the equivalence class of the state and equivalent state we have to find out, right? And once we find out the equivalent state, we have to combine the equivalent state. Means we are reducing the number of state. Initially, suppose Q0, Q1, Q2, Q3 dot 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 up to Q8 states are there. These states are reduced to Q0, Q1, for example. This becomes one state. Then your Q3 becomes another state. Then your Q5, Q7, this becomes second state. So like this way, we have to reduce the number of states. So how that we'll see. The procedure, exact procedure for this. So we can minimize finite automata by finding equivalent states, right? So see here, method for construction of minimum state automata. The steps are given here. So step number 1, first create a set pi 0. So this is pi is nothing but your equivalent class. The pi is called as the equivalent class here. So first we have to create the state that is called as a pi 0, represented by pi 0, that is equal to capital Q1, capital Q2. Q is nothing but your, it is nothing but your set of states, right? Q is nothing but your set of state, capital Q, which consists of your small q0, q1, q2, q3 dot dot dot, right? So you have to represent, or you have to create a pi 0 such a way that it consists q1 and q2. Now what exactly is the q1? Now q1 consists of set of final state and q2 consists of set of non-final state. This is the first important step. Meaning is that you have to separate out the final state. You have to first identify the final state. Say for example q0, okay, sorry, q3 is the final state. So my q1 becomes q3, right? And this capital Q2 becomes rest of all the state that is q0, q1 and q2, for example, and q3 is the final state. This is the first task, or this is the first step in minimizing the automata, right? So pi 0, this is called as a pi 0, or this is called as the equivalent class pi 0, that is equal to capital Q1 comma capital Q2. Capital Q1 is nothing but the set of final state and capital Q2 is nothing but the set of non-final state, right? Clear? Means we have to separate out the final state, and all nine means we have to make a two sets. We have to make a two set. First set consists of your final state, and second state another set consists of all non-final states, right? So see here, step number 2. In step number 2, let Qik be any subset in pi k. Pi k means pi is nothing but equivalent class. So if Q1 and Q2 are in Qik and delta Q1a and Q2a are k equivalent, then Q1 and Q2 are also k equivalent. So find out whether delta Q1a and delta Q2a are residing in same equivalence class pi k. Means we have to find out whether these two states are residing in the same equivalence class. Then it is said that Q1 and Q2 are k plus 1 equivalent. Means it can be said that they are 1 equivalent, or they are 2 equivalent, or they are from 1 equivalent class or 2 equivalent class. This is the step number 2, and we have to repeat the step number 2 for every Qi in and obtain all elements of pi k plus 1. Means step by step we have to go for finding out the equivalence classes, right? In step number 3, construct pi n. Means for n number n equal to 1, 2, 3, we have to construct this equivalence class. And in case of step number 5, then replace all equivalent states in one equivalence class by representative state. Means once you find out the equivalence, so all these steps, what we are getting here from all these steps, we are finding out the equivalent state. Once you find out the equivalent state, from the equivalent state we are easily getting the equivalent class, right? We are easily getting the equivalent class. Initially it is pi 0, then we are going to find out pi 1, and then finally we are going to find out the pi 2. So in this way, and means we are bifurcating, means we are partitioning. Say for example here Q0, Q1, Q2, Q3, initially 4 states are there. We are going to partition these states. Further we are going to partition these states so that up to pi 2 level, means up to equivalence class level number 2, right? So with example, this becomes more clear to all of you. So rules for the minimization. So some important points that we have to remember always while minimizing the automata. So first rule is nothing but replace non-final states by equivalent non-final states, right? Means there are all non-final states can be replaced by the non-final state itself. Replace one final state by equivalent final state, means final state can be replaced by final state only. Do not replace the initial state by any other state. Another important rule is that we have to take care that initial state cannot be replaced by any other state, and do not replace one final state by a non-final state or non-final by one or more non-final states, right? So this thing we have to remember, non-final can be replaced by non-final, as well as the final state can be replaced by equivalent final state only, but initial state cannot be replaced, and do not replace the final state by non-final state, one or more non-final states, right? So see here, let us start with one example. One example is given here. Construct a minimum state automata for the given DFA. Now see the diagram of DFA. How many states are there? There are Q0, Q1, Q2, Q3, Q4. These are the number of states. So total number of states are total 5 states are given here, and the transitions are shown here. So we have to minimize. We have to minimize these number of states. First, we have to find out the which are the states that are equivalent state, right? So first step is to identify the final state, and starting with the final state means we have to see, so final state is Q4, so we have to see which transitions they are coming to the final state on the same input symbol, on the same input symbol, that we have to see. So method we will find, method is first we have to write down the transition table. So transition table, from this transition diagram it is written like this. So Q0 on A go to Q1, Q0 on B go to Q2, Q1 on A go to Q1, Q1 on B, Q3, Q2 on A, Q1, Q2 on B, Q2, Q3 on A, Q1, Q3 on B, it is Q4, and Q4, which is the final state on A input, go to Q1, and Q4 on B input go to Q2 itself, right? So we can write here the final state is Q4. Remember this point. The very first step is to first write the transition table from this given diagram. So always there is a question, minimize the given finite automata. Minimize the finite automata means we have to minimize the number of states here. Whatever maybe the number of states are there, we have to minimize it. So first step is to write the transition table. Yes, it is written. Identify the final state. So Q4 is nothing but your final state. Now what we have to do here, we have to write down the pi 0. Pi 0 is nothing but pi 0 consists of your capital Q1, capital Q2, and capital Q1 is nothing but your Q, means it is a final state, capital Q4, and rest of all other state. See here, just emphasize on this Q2 set. Q2 set you have to see here. So Q1 is first set. Remember, see carefully or listen it very carefully. Q1 is the first set that contain only your final state. That contain only your final state, and remaining all other states, they are belonging to the Q2 set. They are belonging to your Q2 set. Remember this point. This is the first step. So very first step is first write down the transition table, then find out the final state. Once you identify the final state, you have to make the Q1 belong, that is nothing but your final state, and capital Q2 remaining rest of all the state. Rest of all the states means Q0, Q1, Q2, Q3. So Q0, Q1, Q2, Q3. All the states are written in the Q2 itself. Getting this point? Okay. Now we'll proceed further in solving the minimization problem. So see here. Now we will start constructing the equivalence classes. We will start constructing the equivalence classes. So very simple. There is no difficulty, any difficult part here. It's very simple. Just you have to write down the transitions. All the transitions, excluding your final state transition. The transitions of the state belonging to the Q2 set, that we have to write it here. See here, Q0, Q1, Q2, Q3. So how many transitions I have written here? So transition. So second step is that when we have to find out the equivalence class, so take all the states excluding your final state. So I have not written here, that is nothing but your delta q4 a comma b or delta q4 b. This is not written here, means we have to exclude the final state. Means excluding the final state means this belongs to your capital Q1, right? And these all are these states, these are belonging to your capital Q2. So take the states belonging to the Q2 set, and write down their transitions on each input A and input B. So it is very simple. So delta Q0 on A go to Q1 state, delta Q1 on A go to Q1 state, delta Q2 on A go to Q1 state, and delta Q3 on A go to Q1 state. Same with the B input, on B Q0B, Q2, Q1 on B Q3, Q2 on B go to Q2, and Q3 on B go to Q4 state, right? Okay. Now here again I have written Q4 is the final state. Q4 is the final state, and we have to start minimizing our automata. Starting means reverse direction. Reverse direction means what? We are not going to start with the start state Q0, but we have to first take the final state Q4 and we go in the reverse direction. So Q4, where is the Q4? Where is the Q4? We'll find Q4 is here. Q4 is here. So Q3 is only one equivalence state. Means here, so all how many transitions are there? 1, 2, 3, 4, 5, 6, 7, 8. So out of these 8 transitions, only one transition, that is Q3B, that leads to your final state. Only one transition, that is nothing but state Q3 on input B, that go to Q4 state. That's why Q3 is taken away and it is called as a one equivalent state, and it is called as a one equivalent state Q3, right? So pi 1 is equal to, see here, pi 1 equal to this is our initial Q1, that is Q4, that consists of your, that contain your final state, and now Q2, it is divided into these two sets. That Q3 we have removed separately, and the rest of all the states, they remains as it is, and this is called as the one equivalent class. This is called as your one equivalent class. Getting my point or not? Means for what we have written here initially, we have find out here Q1, that is equal to our Q4, and rest of all the states, that is equal to Q2, means Q0, Q1, Q2, Q3. And now after that we have written all the transitions excluding that Q1 class. We have not written the transitions for capital Q1 or small q4, that is nothing but your final state. So Q0, Q1, Q2, Q3, and from this transition we come to know that there is only a single transition, that is delta Q3B, that goes to our final state, which that is nothing but Q4. So we have written a conclusion that Q3 is one equivalent state, and initially this is what is your, this is your pi 0, this is your pi 0. Now we are finding out your pi 1. Pi 1 is nothing but your Q4, which is same as that of initial one, earlier one. Then Q2, this Q2 contains Q0, 1, 2, 3. Now Q3 is separated out. Q3 is separated out here, so it is written in a curly bracket here. See here, it is written in a curly bracket, and rest of all the state, that is Q0, Q1, Q2, they are written in the curly bracket. So this class is called as the one equivalent class. One equivalent class, right? So what we are doing here, we are separating out the states. See carefully, Q4 becomes separated, then Q3 is being separated here. So only states remains are, that is Q0, Q1, and Q2. We have to again partition this Q0, Q1, Q2. See here. Now delta, see here again, write down their transitions Q0, Q1, Q2. So take these states only, Q0, Q1, Q2. Write down their transitions here on both input, on input A as well as on input B, right? So what we'll find here, Q0 on A go to Q1, Q2 on A go to Q1. Now what is this Q1? This Q1 belonging to the single class. Now listen it carefully and see on the screen carefully. This Q1 state belonging to only one class here, belonging to this here Q1, right? And here also Q0 on B, Q2, and Q2 on B, it is Q2. So Q2 is also belonging to one class, right? That's why what we have separated out. So meaning is that Q0 on A go to Q1 and Q2 on A go to Q1, and Q0 on B go to Q2, and Q2 on B go to Q2. That's why what we have written here, see it carefully, states Q1 and Q2 are in the same states. Q1, this Q1, this, so forget about this, and this particular Q2, so forget this, they are in the same state. Hence, what is the conclusion? See carefully. Hence, states Q0 and Q2 means this, they are bold here with a different color. Q0 and Q2, they are called as two equivalent states. They are called as the two equivalent states. Getting this point? They are called as the two equivalent state. Therefore, what we have written here, see it here, pi 2, now we have got here pi 2, that is second equivalent class. And how it is written? So Q4, it is as it is right here. Q3 is as it is from pi 1, and now Q0 and Q1 and Q2. So this particular set is now divided, and what we have separated out? We have separated out your Q0 and Q2 states. These two states we are calling it as a two equivalent states. Q0 and Q2, they are called as a two equivalent states. That's why they are combined together, and one set is prepared for this Q0 and Q2, and Q1 is separate. So ultimately Q1 remains separated one, and it is called as the two equivalent class. This particular is called as the two equivalent class. Getting this point? So see carefully. Initially we are at pi 0, where we have Q1 and Q2. In case of Q1, you have Q4, which is the final state, and rest of the all state Q0, Q1, Q2, Q3 are here. In case of pi 1, we have Q4, we have Q3, means we have separated Q3, and only three states were there. And in case of pi 2, we have Q4 separated, Q3 separated, Q1 separated, and only Q0, Q2 remains as it is, right? And we are calling Q0, Q2 as the two equivalent. Why we are calling it as a two equivalent? Because here the transition Q0 on A go to Q1, Q2 on A go to Q2, means both the states on same input go to the same state. Here also in this B input also, Q0 on B go to Q2, and Q2 on B go to Q2, means Q0, Q2 can be combined here. Q0, Q2 can be combined on B, and they go to Q2, or Q0, Q2 can be combined and on input A they go to Q1 state. Getting this point? So meaning is that we are finding, so that's why we have written here, they are called as the two equivalent state. They are called as the two equivalent states, right? Okay, we'll move to the next point. So here the next line is no further partition is possible. So pi 2 we have written here with the number of sets, and further partition is not possible. Hence the transition table is written like this. So Q0, Q2 is the state we have. So how many states we have received here? We have received here Q0, Q2, then Q1, Q3, Q4, the states remains as it is. And this particular transition, so Q0, Q2, that we have written from our transition function. So Q0, Q2 on input A, it go to Q1 itself. Already we have seen the transition function for this. And Q0, Q2 on input B, it goes to Q2 as well as it goes to Q0 as well as Q2. That's why Q0, Q2. So Q0, Q2, now it is not two state, but it is a combinedly one state. Means Q0, Q2, they are not the two states, but instead of that, it becomes a combined state. It becomes a single state. It is not the two states now. Q0, Q2, it is referred as a single state or only one state now. Q1 is another state, Q3 is the state, and Q4 is the another state. And finally, from this transition table, we have drawn the transition diagram of the minimized finite automata like this. So Q0, Q2, so two states are combined here, Q0, Q2, and see carefully. For minimized automata, we have used the square bracket. So this is the one significance we have to always remember while minimizing the automata. In transition table, we have to write down all the states in the square bracket, as well as while drawing the transition diagram also, the states are drawn in the square bracket itself, square bracket. So Q0, Q2 in the square bracket, then Q1, and then Q3, and Q4 is the state, and Q4 is nothing but it is marked as a star here. It is nothing but your final states, and all the transition Q0, Q2 on A go to Q1, on A go to Q1, Q0, Q2 on B go to Q0, Q2 itself, then Q1 on A go to Q1, and Q1 on B go to Q3 states. So same, all the transitions are represented with the help of this minimize automata. That is, this is the way how we are able to minimize or the reduce the number of states of the given automata. All right. So this is the first example. Now let us see another example so that it will become more clear to all of you. Consider a minimum state construct a minimum state automata for the given DFA or the finite automata Q0, Q1, Q2, Q3, Q4. Q0 is the start state, Q4 is the final state, and the transitions are given on input 0 and 1. So first step is we have to write down the transition table from this automata. So as per the transition diagram, the table is drawn here. And what is the first step? We have to identify the final step. Final step is nothing but Q4, and next is we have to find out the pi 0. So pi 0 is nothing but your two sets, Q1 that consists of your Q4 state, and rest of all other state means rest of non-final state. All these are the non-final state. All these are nothing but this is your final state, and these are called as the non-final state. So Q0, Q1, Q2, Q3, right? And next, on the next slide, there are transitions written on all these states. See here, we are not going to write the transitions for Q4 state, but we are means what we have to do, we have to minimize these number of states. We have to minimize these number of states. Means what generally we are doing here, we are separating Q4 out. Then instead of this in this Q0, Q1, Q2, Q3, Q3, how many state we have to again separate out the number of states so that we are able to minimize, we are able to reduce the number of states, right? So see here, so now we will start constructing the equivalence classes. The same way the transitions are written here, right? And here we have to find out the final state. From in the transition, what we have to look here, we have to only look for the final state, which is the final state. Q4 is the final state. And where we get the Q4 we get here Q4, here is Q4, and here is a Q4. So Q1, Q2, Q3, that's why they are called as the one equivalent state. Very simple. There is no any critical part is involved or no difficulty is involved here. Only we have to see, means we have to look in the reverse direction. We have to look in the reverse direction. So Q4, first we see Q4, and Q4 which transition gives us the final state. So transition of Q3, transition Q2, and transition Q1, they gives us the final state. That's why I directly write in the conclusion that Q1, Q2, Q3, they are one equivalent states. One equivalent state. So bifurcate again these three states. So we write here pi 1 equal to Q4. So Q4 is already separated out, and Q1, Q2, Q3 make it a one set, and remaining is only the Q0. Remaining is only the Q0, right? So this is called, in this particular class, it's called as a one equivalent class. That is nothing but your pi 1. Initially it is pi 0. Pi 0 is now we are converting into the pi 1, right? Now see here, so for Q1, Q2, Q3, we have to write down the transition for Q1, Q2, Q3, means we have to minimize this Q1, Q2, Q3 by writing their transitions here, Q1 0, Q2 on 0, and Q3 on 0, as well as Q1, Q2, Q3 on 1, right? Now what we have to see here, so look carefully here. So from this side, from the output side, we have to always see, so Q2, Q1, Q1, Q2. So Q2 we have to consider Q2, this one Q2, and Q4 is here, and Q4 is here, right? So we can say that this Q2, these two Q2 and this Q4, this belonging to the one set, and this Q4 is belonging to the one set. Getting this point? See carefully, this Q2, these two Q2, first Q2 and this third Q2, as well as this first Q4 and the second Q4, they belong to the one set. Q2 and Q4, they belong to the one set. Hence, Q1. So we can write the conclusion that hence these states Q1, Q3 and Q1, Q3, they are your two equivalent states. They are called as the two equivalent states. Getting this point? See here, the state Q2 is in one set. This state, which is state, this is the set. This is the state. This is the set for Q2. And Q4 is on another set. Q4 is in this particular set, Q4. Hence, states Q1 and Q3 are called as the two equivalent states, right? Therefore, pi 2 equal to Q0. So Q0 is as it is here. Then Q4 is as it is. So Q1 and Q3 we have written separated Q1 and Q3, one equivalent or two equivalent, and Q4 is now separated out. So this is called as the two equivalent class. This is called as the two equivalent class, right? Getting this point or not? So okay, so how we have written this thing? So we have to find out the states, which we have to find out such a states that belonging to the same set. We have to find out the such state that belonging to the same state. So if we look on this particular side, if we look at this particular side, we'll find that q2 is here and q2 is here. It belongs to the one this particular set, right? And we'll find all q4 are there, but no, but we are only looking for this and q0 and q3. So q1 and q3. So q1 and q3, yes. Q4, yes, it also belonging to this one set. This is first set, this is second set, this is third set, this is the second. These are the sets. Pi is nothing but your equivalent classes: first set, second set, and third set. So this q2 belonging to the one set and q4 belonging to the another sets. That's why the what conclusion we have written. So which states gives us that particular set. So this is nothing but, these are nothing but q1, q3. These are the two state that leads us to that particular set, means that gives us that particular set. That's why they are written as a two equivalent. They are written as a two equivalent. So directly write down here pi 2, that is equal to q0 as it is, q2 and q1 q3, combine it. So q1 and q3, instead of two states, now they become a single state. They become a single state here, and q4 is the separated out. So it is called as a two equivalent class. It is called as a two equivalent class, right? So no further partition is possible. No further partition is possible. Hence, transition table is q sigma, and all the transitions we have to write down here. So on q0 on 0 it goes to q1 q3, q0 on 1 goes to q1 q3, q2 on 0 on q1 q3, q2 on 1 goes to q4. Now this becomes your one state, that is q1 q3. On 0 it's q2, and q1 q3 on 1 go to q4, and q4, which is the final state, 0 1 goes to q4 itself. So hence the transition diagram of minimized finite automata is. So from this transition table, the diagram is drawn here. So q0 in a square bracket. So always remember to write the minimized states in a square bracket only. So this is your square bracket state. So q0, q1 q3 is another state, q2 is the state, and q4, which is the final states. 0 1 transitions are here. So one transition from q2 to q4, and the rest of all the transition, and this is your final answer for the minimization of that particular automata, right? Okay, let us go to the next example. Construct a minimum state automata for the given DFA. Now see here how many states are given. So number of states are more here as compared to the previous example. So q0, q1, q2, q3, q4, q5, q6, q7, total number of states are 8. Total number of states are 8, and which is the final state here? Final state is q2 is your final state. So we can have the transition table drawn here. So q0 on 0 1 transition, q1, q2, q3, q4, q5, q6, q7. Total number of states are 8. Number of states are there. So what we have to do here? We have to write down their classes. q1 consists of your final state, that is nothing but your q2, and capital q2 is nothing but your non-final statement, excluding this q2, q0, q1, q3, q4, q5, q7. So all the delta transitions of all these non-final state, we have to find it out. Delta transitions of all these non-final states, right? So same final state is q2. Hence, two sets are being created, that is capital Q1 equal to Q2, that is the final state, and capital Q2 equal to Q0, Q1, Q3, Q4, Q5, Q6, and Q7, right? So see here, now we will start constructing equivalence classes. So same, all the transitions for all these non-final states. These are the transitions for all non-final states. And what we are finding out here, we are finding out which transition goes to the final state, which transition leads to the final state. Q2 is the final state, so find out the transition. So this is one transition that goes to final state. This transition Q7 on 1 go to final state. Q5 on 0 go to final state, and Q3 on 0 go to final state. That's why we write a conclusion. Hence, Q1, Q7. So this one, so Q1, Q7, you have to make one set of these two states, and Q3, Q5, you have to make another set of these two states. They are called as a one equivalent state. These are called as a one equivalent. You cannot make the Q3, Q1 or Q5, Q7 because the inputs are different. We have to consider the input also. So zero input. So meaning is that Q3, Q5. So if you combine Q3, Q5, a logical meaning is that on zero input go to Q2 state. It is very simple or straightforward meaning. Or Q1, Q7 on input 1, it goes to Q2 state. This is very simple. So that's why they are combined, and that they are called as a one equivalent state. That's why they are called as a one equivalent state. So we further write it pi 1 equal to Q2. That is nothing but your final state. And all the non-final states they are partitioned into two sets. This is the first state, this is the first state, this is second state, and the remaining remaining states are in this particular set, right? So now we have to consider the transitions for this Q0, Q4, and Q6 states, right? So see here on the next slide. Now one equivalent class is, so same thing is written here, pi 1 equal to Q2, Q1, Q7, Q3, Q5, and another set. So this is called as, so that's why they are written. So here, that's why they are written in a curly brackets. That's why they are written in a curly brackets. Q2 is a one set, Q1, Q7 is another set, this Q3, Q5 is the third set, and Q0, Q4, Q6 is the fourth set, third set, second set, and this is the set number 1. So for what we have to find out the transitions, we have to find out the transition for this state Q0, Q4, and Q6. So the same is written here, Q0, Q4, Q6, and there are transitions on 0 input and the 1 input. Right now we have to again look into this particular here Q1 and Q7. So where is the Q1 and Q7? So Q1 and Q7 they belonging to this particular set. See carefully, how we are moving to the two equivalent class, or how we can call the state as a two equivalent state, right? See on this right hand side RHS of that particular transition Q1 Q7 they belong to the same set. That's why Q0 Q4 we can combine together, and we call it as a two equivalent state, right? Here also on this side also Q5 belonging to the same class. So Q0 Q4 you can have one as input and they go to Q5, means you can combine this Q0 Q4 and you can call it as a two equivalent states. You can call it as a two equivalent state, and here also Q0 Q4 you call it as a two equivalent state, right? So the same thing is written here. Hence states Q0 Q4 are two equivalent. Getting this point? So pi 2 means further we partition this. So partition is Q2 is the one set, Q1 Q7 is another set already given, Q3 Q5 is the third set, and Q0 Q4 is the new set is created, and the left is Q6 is the single state is remaining. So there is no need to further partition, or we cannot partition further. So it is written here. So no further partition is possible, and the transition table is written here with the number of states Q0 Q4. So first this state is written here Q0 Q4, then Q1 Q7, because our sequence is 0 1 2 3, then 4 is already gone here, then 6 5 is gone, 6 is here written here, and 7 and Q2 is nothing but our final. Q2 is nothing but the final state. Q0 Q4 on 0 goes to Q1 Q7. So see here Q0 Q4 on 0 goes to Q1 Q7. So that's why it is written here Q1 Q7. Now Q0 Q4 on 1 goes to Q5 only, but Q5 there is no such a state Q5 here. Q5 always comes with Q3 because Q3 Q5 we are combined. That's why it is written here Q3 Q5. Remember this point. This you have to take a precaution while finding out the transition, because yes, no doubt Q0 Q4 they go to Q5 state. Q0 Q4 on one input they go to Q5. But in this state there is no Q5 now. It remains as a single state. It combines with Q3. That's why Q3 Q5 it is written here, and that is correct. Now Q1 Q7 on input 1 it goes to Q6, and on input 0 goes to Q6, and on input 1 go to Q2. In the same way we have to write down all the transitions, and once you write down all the transition in the transition table, then it becomes very simple to draw the transition diagram of the minimized finite automata. So see here, hence the minimized DFA is drawn here. So see all the states, they mark with the square bracket, right? And the transition as given in the transition table, all are marked correctly, and this is our final, and that is called as the correct minimization of the given automata. Correct minimization, or we have reduced the states. So how many states we have reduced? We have reduced these Q4 states. One Q4 is we have reduced, Q7 is reduced here, and Q5 means 3 states we have reduced here. Instead of 8, now it becomes 5 state automata. In the given question, it consists of 8 number of states, but here in the answer, now it consists only 5 number of states. Getting this point? Okay. Let us go to the next slide. The next example, construct a minimum state automata for the given. So see here, so how many number of states? That is Q0, Q1, Q2, Q3, Q4, Q5, Q6, and Q7. Again, 8 states are there. Again, 8 states are given, and we have to write down the first step. We have to write down the transition table from this diagram. This is the solution. And final state is Q3. The final state we have identified here, and this is nothing but our Q3. So separate it out. This becomes your capital Q1, and rest of all other states, they becomes your capital Q2. And we have to write down the delta transitions for all capital Q2 states. Delta transitions for all capital Q2 states, and we have to see which states leads to our final state. That is nothing but your Q3. And that states we are calling it as a one equivalent class, or that states we are making it as a one equivalent states, right? So final state is Q3. Very simple. There is no difficult part involved here. It is very simple. Only the thing is that you have to just remember the steps. Once you remember the steps, then it is very simple, very easy part. Hence the two sets are capital Q1, that is equal to Q3, and non-final states are Q0, Q1, Q2, Q4, Q5, Q6, Q7. Q3 is not written because it is in another set. So see here, now we will start constructing the equivalence classes. So for all the non-final state, so Q3 is the final set. So just find out where is the Q3. So Q3 I will find here on Q7. So here there is no Q3. So on here also these are the states that gives me the Q3 states, right? So Q2, Q4, Q7, they are called as the one equivalent state. Q2, Q4, Q7, they are called as the one equivalent, and you can combine these two states, Q2, Q4, combine and becomes a one set. It becomes a one set for Q2, Q4, but Q7 there is no other state is there. That's why Q7 is the single one. So Q7, this becomes another set. This is another set. To two sets you have find it out here are one equivalent states. They are one equivalent states. Hence pi 1, Q3 as it is initially state, then Q7 from here, then Q2, Q4 is here. Okay, so we have remaining only Q0, Q1, Q5, Q6. These four states, these are the four states, Q0, Q1, Q5, Q6, they are the remaining state. Means we have to further partition these four states, right? We have to further partition this, and we have to only consider the delta transitions for these states only. So let us see on the next slide. So pi 1 is equal to, same thing is written here, Q3, Q. So on always write in a curly bracket, always write in a curly bracket, Q3, Q7, then bracket Q2, Q4, and in the bracket Q0, Q1, Q5, Q6, one equivalent class. Now start constructing the equivalence class for two equivalent states, right? So for Q0, Q1, Q5, and Q6, right? So here, so what we have to find out here. So see on this particular side, on the right hand side here. So Q0 and Q6, Q0 and Q6. So Q0 is here and Q6 is here. That belonging to the same state, because this belonging to the same state number 4, right? Right. And here Q2, Q4, Q2 and Q4. So Q2, Q4, this belonging to the another set, right? Q2, Q4. Hence, we can write a conclusion that Q1, Q5, you combine this Q1, Q5 as one state. So here states Q0, Q6 are in one set and Q2, Q4 are in another set. Hence, the states Q1, Q5 are two equivalent states. Hence, they are called as the two equivalent states. Remember this, right? Hence, they are called as a two equivalent states. So pi 2 we have written here, Q3 as it is, Q7, then Q2, Q4 it is taken as it is, and one new set we have find it out, that is Q1, Q5, it is written here, and the remaining is Q0, Q6, and this further distribution or further partition is not possible here. So this becomes your one state, third, second, third, four, and this five. How many state it becomes now? It becomes five state DFA. This becomes your five state automata. And see the transition table. So no further partition is possible here, and the transition table is written here. So Q sigma inputs A and B. So Q0, Q6 on input A, Q0, Q6 on input B, go to the states, right? And from this transition table, the transition diagram is drawn. That is nothing but your minimized finite automata. So Q3 being the final state, it is marked with a double circle. Start state is Q0, Q6. So Q0, Q6, Q1, Q5 is written here. Then Q2, Q4, Q2, Q4 is here. Q3 is written here, and Q7 is Q7. Okay, and all the transitions are written, and this is your final state. So initially in the given diagram, the 8 states were there, but now it consists of 5 states only. So we have reduced the 3 number of states, that is Q6, Q5, and Q4. These 3 states we have compressed it, we have reduced it, getting this point. And with the proper method, with the one, first we have find out the final state, then we find out the one equivalent class, then one equivalent state we have find it out, then we find it out the second equivalent class and second equivalent state. Getting this point, that is pi 0, pi 1, and pi 2, right? Okay, so let us construct a minimum state automata for the following DFA or the following automata given here. So this question is for assignment or for your homework. So there are total number of 8 states are given, capital A, B, C, D, E, F, G, and H. The transitions are shown here. So step by step, step by step, you have to solve it, and you have to get the final minimized automata for the given question. The same type of question asked in the in semester as well as the end semester examination. You have to minimize the number of states, right? And we have to follow the same methodology, which I have explained in the slides, right? Okay, so the course outcomes. So the what we have learned in this today's session is nothing but the minimization of finite automata. It's very simple. There is no difficult part involved, but only the thing is that you have to remember the steps how to minimize the automata. The course outcome is nothing but to construct the finite state machines to solve the problem in computing. And the reference book, as usual, you have to only refer the standard reference book. Okay, so let us stop here for this today's session.